Now it's time to take a closer look at RC circuits, circuits with both resistors and capacitors. We've been thinking about capacitors as charging instantaneously when we hook them up to a battery. Of course, it takes a little bit of time for electrons to move around the circuit and fill up the plates of the capacitor, and for that capacitor to reach its maximum charge. Here's a simple circuit. We call this an RC circuit because it has a resistor and a capacitor in series with our battery. I also put a switch in this circuit. When we close the switch, the battery starts to move charges around from one plate of the capacitor to the other. Of course, this is an open circuit right here. There's no electrical connection between the plates of the capacitor. So after a long time, the current in this circuit has to be zero. It's an open circuit. But for a very short period of time, when we close the switch, charges will move from one plate to the other plate. If you like thinking about positive charges moving, we know they don't move, but that's okay. We can think about it that way in this circuit. The positive charge moves around through the battery to the top plate of the capacitor. If you prefer to think about it the proper way with electrons moving, the electron gets removed from the top plate, leaving a positive charge behind, gets moved through the battery to the lower plate, and gets deposited there. And this happens fairly quickly at first. As the charge builds up on those plates, it becomes harder and harder for the battery to push more charge onto those plates because those electrons are all repelling each other. And the rate at which the capacitor is charging slows down. So let's see if we can think of a couple of things that would affect how quickly that capacitor reaches its maximum charge. One thing that would depend on is the size of that capacitor. If you have a small capacitor, it's not going to take the battery as long to charge it up as if you had a capacitor that could store lots of charge. What else would have an effect on charging this capacitor? The value of this resistor. The smaller that resistor, the easier it is for the battery to move charges through the circuit. The bigger the resistor, the harder it is to move charges through the circuit. So that resistor is going to have some impact also. Let's take a closer look at the charging of a capacitor in a circuit like this and see what the equations end up telling us. Let's look at a little timeline of what happens in this circuit after we close the switch and that capacitor begins to charge. Here we are before we close the switch. There's no charge on that capacitor. There's no movement of charges, no current in the circuit. This is our starting point. Now we're ready to close that switch. We've just closed the switch. Current begins to move through the circuit in this direction. And that means the capacitor begins to charge. Positive charge on the upper plate, negative charge on the lower plate. And our final image is after that switch has been closed for a long time. The capacitor is fully charged, and so the current stops at that point. And we have plus Q on the upper plate and minus Q on the lower plate. I'll use capital Q for the final charge that's not changing anymore, and lowercase in the center image here, lowercase q, means that the charge is changing at that point. We can apply the loop rule to this circuit, and we get the rise of potential through the battery minus the drop through the resistor minus the potential drop across the capacitor. What's the potential drop across a capacitor? Q over C, and we're back to where we started. Q and I both vary in time. And there's a relationship between them. We can rearrange this equation And physics instructors like to multiply both sides by dt and integrate. I know your math instructors don't like it when we do that, but we like to do that in physics. And so when we do that, we end up with a differential equation, and the solution to that differential equation ends up being something like this. That's for the charge as a function of time on our capacitor. But we could also get the current as a function of time in our circuit by taking the derivative of this with respect to time, because I is dq dt. This is just the maximum current we get if we put in t equals 0. That's the initial current, that big surge of current we get at the instant we close the switch. And then it dies down after that because charge is building up on the plates of the capacitor, and it starts to push back and resist the charges, new charges, from coming onto those plates. So the maximum current we get occurs at t equals 0. It's always a good idea to check to make sure you got your equations correct, because we have an equation for a charging capacitor and we have an equation for a discharging capacitor. In this case, our capacitor is charging. Because our capacitor is charging up, it started out with no charge at t equals 0. Let's plug in t equals 0 into our equation and see what we get. If we put t equals 0 in here, we just get e to the 0 power, which is 1. 1 minus 1 is 0. So we get 0 charge on our capacitor, which is good. When it started out, when we closed that switch, the instant we closed the switch, there was no charge on the capacitor. What happens at t equals infinity? We should get to our maximum charge. So if we put in t equals infinity, we get e to the minus infinity is 0. And so we get 1 minus 0 is 1, and we just get capital Q. At t equals infinity, the charge approaches capital Q, our final charge. So this looks like the correct equation. At least the limits give us what we're expecting. What does it look like when we graph it? We start out at 0, and as time approaches infinity, it approaches its maximum charge. We could also look at the current in the circuit. At the instant that switch closes, the current starts out at its maximum value, E over R. And as time goes on, as time approaches infinity, this current approaches 0. Now, we like to be able to compare our circuits. If I have a circuit with a resistor and a capacitor, and you have a circuit with a resistor and capacitor, we want to be able to compare them. You know, how long does my capacitor take to charge up? How long does yours take to charge up? Well, technically, they both take an infinite amount of time to charge up. So infinity and infinity, we can't tell the difference between our two capacitors. But what we can do is see how long it takes to get to some other charge, maybe half of its maximum charge. I could say, well, mine takes 40 milliseconds to get to half of its maximum charge. And you could say, oh, mine takes 20 milliseconds to get to half of its maximum charge. Then we would know that yours charges up faster than mine does. But half isn't a nice number that falls out here. We're dealing with exponents and e to the t over rc power, and to find the time that the charge is half of its maximum value is not very obvious by looking at this equation. So instead, we say let's find the time for it to drop to 1 minus 1 over e of its maximum value. We say what time, when is this a really nice, easy thing to spot here? When does this equation become sort of something that's easy to spot? Well, when t is equal to rc, we just have e to the minus 1. So that's something that's kind of easy to deal with. So we say that for a charging capacitor, when t is equal to rc, the charge is equal to 1 minus 1 over e of its maximum charge. So if we look that up on our graph here, if this is rc, the time is equal to rc, then this would be 1 minus 1 over e of its maximum value if this is Q max. That's something we can compare pretty easily, and it falls right out because of the equation. Maybe it's a little more obvious with the current. What value can we spot easily for the current that gives us something we can solve for and compare our circuits? Well, I can see that when my current is 1 over e of its maximum value, that occurs when t is equal to rc. So when t equals rc in this equation for current, I get this is just 1 over e times my maximum current. Now we can compare that. We call that the time constant of the circuit. And we say that's equal to tau, the time constant. So if I tell you my circuit has a time constant of 40 milliseconds, you know how long it takes my capacitor to charge up to 1 minus 1 over e of its maximum charge. And if you tell me yours has a time constant of 20 milliseconds, I know yours gets to that value faster than mine does. Now let's look at the case where our capacitor is charged and it's ready to discharge through a resistor. Here's a timeline of what might happen if we hook up a capacitor and a resistor. In our first image, the switch is open. The capacitor is fully charged. The upper plate has negative Q and the lower plate positive Q charge. But nothing's happening because that switch is open. No current is flowing. Let's close that switch. With the switch closed, current begins to flow in this direction. The capacitor is still charged, but the charge is changing. And if we wait long enough, we get this. The current stops, and our capacitor is discharged. If we apply the loop rule, and using I is dq dt, we get a differential equation, and the solution to that differential equation for charge as a function of time is the maximum charge times e to the minus t over rc. And for the current, let's think about this for a second. When t is 0, we get our capacitor is fully charged. Put 0 in for t. we get e to the 1 power. So Q as a function of time is just the full charge on our capacitor. That's what we started with, right? The capacitor fully charged. That makes sense. And put t equals infinity in there, and you get 1 over e to the infinity power, which is 0. So the charge approaches 0 as t approaches infinity. Now, the minus sign in front of the current here indicates that the direction is opposite the direction that was used to charge the capacitor. So again, we call the time constant tau R times C. And tau tells us, the time constant tells us how long it's going to take us to charge our capacitor to a certain percentage of its maximum capacity, or for it to discharge a certain percentage of its maximum charge. And it makes sense that it would be R times C, because at the very beginning of this video I asked, what do you think it would depend on for this charge is to move around through the circuit and build up on that capacitor? And one of the things we decided it would depend on was the size of that capacitor. The bigger the capacitor, the longer the time it's going to take. And so we have this dependence here on capacitance. And the other thing we decided would affect it is the resistance in the circuit. And the bigger the resistor, the longer the time it's going to take, because it slows the flow of charges through the circuit. And so we have the resistance times the capacitance as our time constant.